This class addresses the remainder of methods of class ZCL vector which are comparable with Python's numpy. The remaining methods are a nice extension of functionality allowing the user to execute a toString method to receive the vector in Python's notation, the shape method which is the equivalent of Python's, and a method to transpose the vector useful for matrix manipulations. The vector class on itself is presented which showcases the methods mentioned herein. This class focuses on vector addition, multiplication, dot and cross products and their equivalent calls in numpy. It's a very cool topic, so stick around. Now is a good time to subscribe and give us a like if you appreciate the content of this project. As seen in Class 1, the vector support is used on matrix compositions as well as on vector operations. As before, we will use the REST API written in ABAP to invoke the class methods from Python. Without further ado, let's look at the vector addition runtimes of the ABAP linear algebra's vector solution and numpys. The series of graphs shown are the runtimes of the ABAP linear algebra vector class executing the same protocol we applied on Class 1. For 100 iterations, we will create vectors of ranks 2 to 200,000. From left to right we progress the tests running 100 times each rank and checking the effect on the runtime. Comparing to vector creation, vector addition seems more quasi-linear where, as we run multiple times and memory is allocated from the heap, we see a slow degradation of performance where the runtime varies between 300 milliseconds and 950 ms. The class averages 600 milliseconds of runtime which is comparable with vector creations. The graph shown is the overlay of the previous graphs. Note the clear spikes at the beginning and ending of the series. The culprit seems to be the garbage collector since there is nothing specific about vectors of rank 2 and of rank 200,000 that would justify the longer spike at the end. The spikes in the beginning could be associated as a side effect of previous operations and garbage collector influences. It is noteworthy to appreciate the slow raise in runtime bounded by the 5 slice of operations. As memory becomes a scarce commodity, runtimes do increase significantly. The next series of graphs shown are the runtimes of numpy's vectors implementation executing the same protocol as before. In here, however, we observe that numpy has a clear parabolic shape curve on all but one rank, but nevertheless managed to yield a runtime bounded by 70 milliseconds until rank 200. Starting at rank 2000 we see a clear degradation of resources, where the starting runtime is near the peak of the previous set, and maxing at 250 ms. This is a substantial change, over 70% of previous noted runtimes. It seems that, from this moment onwards, numpy began to demand more resources, forcing the runtime to jump by a factor of 100% when compared with rank 20,000, and astonishingly by a factor of 800 at rank 200,000. The overlaid graph shows a better picture clustering the runtimes up to rank 2000 at near optimal levels. Just as the previous graphs demonstrated, starting at rank 20,000 the cost of allocation becomes a nuisance, when the runtime stabilized at 500 milliseconds, and valleys at 4 seconds at rank 200,000. Part 2 tackles the dot product process of two vectors yielding a scalar. The series of graphs shown are the runtimes of ABAP vectors dot product executing the same protocol as before. In here, we again observe the adherence with the two previous graphs where the extrapolation could be either linear or quadratic. In lines with previous tests, the ABAP solution maintains parity between tests, and on this method, its maximum runtime is 500 milliseconds. There seems to be no resource depletion at SAP's application server, given that the runtimes are bounded from 200 milliseconds to 500 milliseconds, a nice variation showing a good performance. As dot products are constantly used in data sciences, have a strong algorithm implementing it is to the advantage of the library. For smaller ranks, the dot product executes in its original algorithm, but for ranks 2000 and higher, it applies a divide-and-conquer algorithm. The overlaid graph shows a better picture clustering the runtimes all the way through the process. It is worthwhile to mention that this particular cluster is very similar to the vector addition one with steady consumption of resources as the number of iterations grows. A curiosity is that, yet again, Rank 2000 seems to have the best usage of resources and lower runtime, a fact we should investigate further. The series of graphs shown now are the runtimes of numpy's vectors.product executing the same protocol as before. Observe the process at rank 2, which gives us a good understanding of the solid implementation of .product in numpy for lower bound range from 1 millisecond to 80 milliseconds. Starting at rank 2000, however, there is, again, a double of the previous runtime to 140 milliseconds. It also valleys near the peak of the last three graphs. At larger ranks, the degradation is now severe. For rank 20,000 it maxed at 1.4 seconds, and for 200,000 it maxed at 5.5 seconds. There seems strange and caught us by surprise as an unexpected behavior of a C module super-optimized multi-threaded code. The overlaid graph, a bit boring to say the least, showcases the explanation above. The runtime's REO isn't indeed quasi-constant, with the upper graphs colliding against the one for rank 2000 and therefore not visible. Note the jump in resource depletion at rank 200,000. As before, there is nothing special about .product of rank 2, so the spurious spike is again a manifestation of the pesky garbage collector interfering in our measurements. The last series of graphs shown the extraordinary efforts placed by the authors of the ABAP linear algebra library when a cross product on Rn by Rn is made available. The graph sequences, as expected, follow the trend of the last two tests with performance runtime metrics between 220 milliseconds and 700 milliseconds, once more averaging on the 600 milliseconds level. As strange as it sounds, numpy, a scientific library, does not provide support for cross-product over non-Euclidean spaces. Granted, this is a very complicated algorithm, and implementing it in ABAP using recursive calls was nothing but a state of art. Let's pause and focus on the last graph, which is the Rn space cross-product. This is the equivalent of a vector multiplication but in n dimensions, using Laplacian column normalization for each dimension, and the matrix of determinants. Some argue that for cases when the vector's dimensions are not equal, it is just a matter of adding a unit normal vector to the missing dimensions, but this has never been widely accepted. The series of tests conclude with the overlaid graph with a cross product on ABAP depicting the shockingly excellent runtime achieved by this library using the humble ABAP. Lastly, we provide a bird's eye view of all overlays for the sake of comparison. The Python's code. And finally, the ABAP API calls used.